Current primarily flows from a source, such as a generator or transformer, to a load, such as an appliance or a light bulb, in a closed circuit. However, in electrical systems, there are also stray currents that leak to ground due to imperfections in insulation and other factors. Considering a ground fault, the fault current indeed travels back to the main panel through the ground path. In the event of a ground fault, there is a low resistance path to ground from a phase conductor, allowing current to flow into the ground. This causes the voltage at the fault location to drop to near 0 volts. When this happens, the neutral conductor, which is normally at a voltage near 0 volts, now becomes the current-carrying conductor. This results in a high current flow through the neutral back to the main panel, where it trips the breaker because the current exceeded the breaker's rating. However, for a short circuit, the fault current does not typically flow through the ground path. Instead, it flows directly between two phase conductors or between a phase conductor and a grounded surface, creating a high current flow. This high current flow causes the breaker to trip due to overcurrent. Current generally seeks a path to ground, but this is not always the only path it takes. In the case of ground faults, the fault current does flow back to the main panel through the ground path and triggers the breaker. However, in the case of short circuits, the fault current typically flows directly between conductors, causing the breaker to trip. In a grounded electrical system, the neutral conductor is intentionally connected to ground at the service entrance. This connection provides a low impedance path for fault current to return to the source, which helps to quickly trip the circuit breaker or fuse and clear the fault. The ground rod is used to provide a connection to the earth, which helps to stabilize the voltage of the electrical system and provide a path for fault current to flow back to the source in the event of a ground fault. The ground rod is typically connected to the grounding electrode conductor, which is then connected to the neutral busbar in the main electrical panel. When a ground fault occurs, the fault current flows through the grounding electrode conductor, the ground rod, and the earth back to the source. This flow of current helps to quickly trip the circuit breaker or fuse and clear the fault. The size of the grounding electrode conductor and the ground rod must be sized according to the National Electrical Code (NEC) to ensure that they can safely carry the fault current. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The NEC also specifies the minimum size and length of the ground rod. In addition to the grounding electrode conductor and the ground rod, there are other grounding requirements in the NEC that must be followed to ensure the safety of the electrical system. These requirements include the bonding of all metal enclosures, such as electrical panels, junction boxes, and equipment frames, to the grounding system. Bonding helps to create a low impedance path for fault current to flow back to the source, which helps to quickly trip the circuit breaker or fuse and clear the fault. It's important to differentiate between ground faults and short circuits because they involve different current paths and protective mechanisms. A ground fault occurs when an ungrounded conductor comes into contact with a grounded surface or equipment grounding conductor. This creates a path for current to flow back to the source through the grounding system. Ground fault circuit interrupters, or GFCIs, are designed to detect ground faults and quickly interrupt the circuit to prevent electrical shock. A short circuit, on the other hand, occurs when there is a direct connection between two ungrounded conductors or between an ungrounded conductor and a neutral conductor. This creates a very low impedance path for current to flow, resulting in a high current flow that can damage equipment and cause a fire. Circuit breakers and fuses are designed to protect against short circuits by interrupting the circuit when the current exceeds a certain level. The path of fault current during a ground fault is as follows. Firstly, a fault occurs when an ungrounded conductor comes into contact with a grounded surface or equipment grounding conductor. Secondly, fault current flows from the ungrounded conductor through the fault to the grounded surface or equipment grounding conductor. Thirdly, the fault current flows back to the source through the grounding system, including the equipment grounding conductor, the grounding electrode conductor, and the grounding electrode. Fourthly, the circuit breaker or fuse trips, interrupting the circuit and stopping the flow of fault current. The path of fault current during a short circuit is different. Firstly, a fault occurs when there is a direct connection between two ungrounded conductors or between an ungrounded conductor and a neutral conductor. Secondly, fault current flows from one ungrounded conductor to the other ungrounded conductor or to the neutral conductor. Thirdly, the fault current flows back to the source through the ungrounded conductors. Fourthly, the circuit breaker or fuse trips, interrupting the circuit and stopping the flow of fault current. The NEC, or National Electrical Code, provides detailed requirements for grounding and bonding electrical systems to ensure safety. Grounding and bonding help to create a lower impedance path for fault current to flow back to the source, which helps to quickly trip the circuit breaker or fuse and clear the fault. The NEC also specifies the size and type of conductors that must be used for grounding and bonding, as well as the methods for installing these conductors. Some of the key NEC articles related to grounding and bonding include Article 250, which covers grounding and bonding in general, Article 250.24, which covers grounding of service equipment, Article 250.50, which covers grounding electrode systems, and Article 250.118, which covers types of equipment grounding conductors. When dealing with electrical systems, it is crucial to understand the concepts of impedance and fault current. Impedance is the total opposition to current flow in an alternating current (AC) circuit, and it includes both resistance and reactance. Fault current is the current that flows during a fault condition such as a short circuit or a ground fault. The magnitude of the fault current depends on the impedance of the fault path. A lower impedance fault path will result in a higher fault current. The available fault current at a particular point in an electrical system is the maximum amount of current that could flow during a fault condition. This information is important for selecting and installing overcurrent protective devices such as circuit breakers and fuses that are capable of safely interrupting the fault current. Calculating fault current involves determining the impedance of the fault path and then using Ohm's law to calculate the current flow. The impedance of the fault path includes the impedance of the conductors, transformers, and other equipment in the circuit. There are several methods for calculating fault current, including the point-to-point method and the infinite bus method. The point-to-point method is used to calculate the fault current at a specific point in the electrical system, while the infinite bus method is used to calculate the fault current at the service entrance. Overcurrent protection is a critical aspect of electrical safety. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect electrical circuits and equipment from damage caused by excessive current flow. Circuit breakers are electromechanical devices that automatically interrupt the circuit when the current exceeds a certain level. Fuses are one-time devices that melt and interrupt the circuit when the current exceeds a certain level. The selection of overcurrent protective devices is based on the ampacity of the conductors and the rating of the equipment being protected. The NEC provides detailed requirements for the selection and installation of overcurrent protective devices. Some of the key NEC articles related to overcurrent protection include Article 240, which covers overcurrent protection in general, Article 240.4, which covers protection of conductors, and Article 240.6, which covers standard ampere ratings for fuses and circuit breakers. Ground fault circuit interrupters, GFCIs, are designed to protect people from electrical shock by detecting ground faults and quickly interrupting the circuit. A ground fault occurs when there is an unintended path for current to flow to ground, such as when a person comes into contact with a live wire and a grounded surface. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference of more than 5 mA between the current flowing in the hot and neutral conductors, the GFCI will trip and interrupt the circuit. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. Arc fault circuit interrupters (AFCIs) are designed to protect against fires caused by arcing faults. An arcing fault occurs when there is an unintended arc of electricity between two conductors or between a conductor and a grounded surface. Arcing faults can generate a lot of heat and can easily ignite nearby combustible materials. AFCIs work by monitoring the electrical current for characteristics that are indicative of arcing faults. If an arcing fault is detected, the AFCI will trip and interrupt the circuit. AFCIs are required in many locations, such as bedrooms and living rooms, where there is a high risk of fires. The coordination of overcurrent protective devices is important to ensure that the overcurrent protective device closest to the fault will trip first, minimizing the extent of the outage. Coordination involves selecting and setting the overcurrent protective devices so that they will trip in a coordinated manner. The time current curves of the overcurrent protective devices must be coordinated to ensure that the device closest to the fault will trip before any upstream devices. Selective coordination is a more advanced form of coordination that ensures that only the overcurrent protective device closest to the fault will trip, even under high fault current conditions. Electrical safety is paramount when working with or around electrical systems. Following safe work practices, wearing appropriate personal protective equipment, and using properly maintained tools and equipment are essential for preventing electrical accidents. Some of the key electrical safety practices include energizing electrical equipment before working on it, using lockout-tagout procedures to prevent accidental energization, wearing appropriate personal protective equipment such as rubber gloves and safety glasses, and using properly insulated tools and equipment. Regular inspections and maintenance of electrical systems are also important for identifying and correcting potential hazards. The NEC provides detailed requirements for electrical safety, and it is important to follow these requirements to ensure the safety of people and property. Understanding the difference between the grounded conductor, which is the neutral, and the equipment grounding conductor, which is the ground wire, is crucial for safety and proper system operation. The grounded conductor, or neutral, is intentionally connected to ground at the service entrance and carries current under normal operating conditions. The equipment grounding conductor, or ground wire, is connected to the metal enclosures of electrical equipment and does not carry current under normal operating conditions. The purpose of the equipment grounding conductor is to provide a low impedance path for fault current to flow back to the source in the event of a ground fault. Separating the grounded conductor and the equipment grounding conductor helps to prevent electrical shock and ensure that the overcurrent protective devices will trip quickly in the event of a ground fault. The NEC requires that the grounded conductor and the equipment grounding conductor be kept separate except at the service entrance. Surge protection is used to protect electrical equipment from voltage surges, which are transient overvoltage events that can damage or destroy sensitive electronic equipment. Voltage surges can be caused by lightning strikes, power line switching, or other electrical disturbances. Surge protective devices, SPDs, are designed to divert the surge current away from the protected equipment and back to the source. SPD are typically installed at the service entrance and at the point of use. The selection of SPD is based on the voltage and current rating of the electrical system, as well as the level of surge protection required. The NEC provides detailed requirements for surge protection, and it is important to follow these requirements to ensure the protection of electrical equipment. Harmonic distortion is a phenomenon that can occur in electrical systems due to the presence of nonlinear loads, such as electronic equipment, variable frequency drives, and compact fluorescent lamps. Nonlinear loads draw current in a non-sinusoidal manner, which creates harmonic currents that can distort the voltage waveform. Harmonic distortion can cause a number of problems, including overheating of transformers and conductors, malfunction of sensitive electronic equipment, and increased energy losses. Mitigating harmonic distortion involves using harmonic filters, which are designed to block or reduce the harmonic currents. Harmonic filters are typically installed at the source of the harmonic distortion, such as at the output of a variable frequency drive. Power quality is a measure of the quality of the voltage and current in an electrical system. Poor power quality can cause a number of problems, including equipment malfunction, increased energy losses, and reduced system reliability. Power quality problems can be caused by a variety of factors, including harmonic distortion, voltage sags, voltage swells, and transient overvoltages. Improving power quality involves identifying the source of the power quality problems and then implementing appropriate solutions, such as harmonic filters, voltage regulators, and surge protective devices. Electrical metering is used to measure the amount of electrical energy consumed by a building or facility. Electrical meters are typically installed at the service entrance and measure the voltage, current, and power factor of the electrical system. The data from the electrical meters can be used to track energy consumption, identify energy waste, and optimize energy efficiency. Advanced Metering Infrastructure (OMI) is a system that uses smart meters and communication networks to collect and transmit electrical metering data in real time. AMI can provide a number of benefits, including improved energy efficiency, reduced energy costs, and enhanced grid reliability. Energy efficiency is the practice of using less energy to provide the same level of service. Improving energy efficiency can save money, reduce greenhouse gas emissions, and enhance energy security. There are many ways to improve energy efficiency, including using energy-efficient appliances and equipment, insulating buildings, and using renewable energy sources. Energy audits can be used to identify energy waste and develop strategies for improving energy efficiency. Renewable energy sources, such as solar, wind, and hydropower, are becoming increasingly popular as a way to reduce reliance on fossil fuels and reduce greenhouse gas emissions. Renewable energy sources are sustainable and environmentally friendly. Solar power uses photovoltaic cells to convert sunlight into electricity. Wind power uses wind turbines to convert wind energy into electricity. Hydropower uses dams to convert the energy of flowing water into electricity. Energy storage is used to store electrical energy for later use. Energy storage can be used to improve grid reliability, reduce energy costs, and enable the integration of renewable energy sources. Batteries are the most common form of energy storage. Batteries store electrical energy in chemical form and can discharge the energy when needed. Other forms of energy storage include pumped hydro storage, compressed air energy storage, and thermal energy storage. The NEC is updated every 3 years to reflect changes in technology and industry practices. Staying up to date with the latest NEC requirements is essential for ensuring the safety and reliability of electrical systems. The NEC is available from the National Fire Protection Association, NFPA. Electrical codes and standards are developed by organizations such as the NFPA, the Institute of Electrical and Electronics Engineers, IEE, and the American National Standards Institute, ANSI. These codes and standards provide detailed requirements for the design, installation, and maintenance of electrical systems. Following these codes and standards is essential for ensuring the safety and reliability of electrical systems. Electrical inspections are conducted by qualified electrical inspectors to ensure that electrical installations comply with the NEC and other applicable codes and standards. Electrical inspections are typically required for new construction, renovations, and repairs. Passing an electrical inspection is essential for obtaining a certificate of occupancy and ensuring the safety of the electrical system. Electrical safety training is essential for anyone who works with or around electrical systems. Electrical safety training teaches workers how to identify and avoid electrical hazards, how to use safe work practices, and how to respond to electrical emergencies. Electrical safety training is required by OSHA for many types of electrical work. Arc flash hazards are a serious electrical safety concern. An arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical system. Arc flashes can cause severe burns, electrical shock, and even death. Arc flash hazard analysis is used to determine the potential arc flash hazards in an electrical system. Arc flash hazard analysis involves calculating the incident energy and the arc flash boundary. The incident energy is the amount of energy that a worker would be exposed to during an arc flash. The arc flash boundary is the distance from the arc flash source at which a worker would be exposed to a dangerous level of incident energy. Personal protective equipment (PPE) is used to protect workers from arc flash hazards. PPE includes arc-rated clothing, gloves, and face shields. The type of PPE required depends on the incident energy level. Lockout-tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. Lockout-tagout procedures involve disconnecting the electrical equipment from its power source and then attaching a lock and tag to the disconnect switch. The lock and tag prevent anyone from accidentally energizing the equipment while it is being worked on. Electrical troubleshooting is the process of identifying and correcting electrical problems. Electrical troubleshooting requires a thorough understanding of electrical circuits and the ability to use electrical test equipment. Common electrical problems include open circuits, short circuits, ground faults, and voltage drops. Electrical test equipment is used to measure electrical parameters such as voltage, current, resistance, and continuity. Common electrical test equipment includes multimeters, clamp-on ammeters, and circuit tracers. Multimeters are used to measure voltage, current, and resistance. Clamp-on ammeters are used to measure current without having to disconnect the circuit. Circuit tracers are used to trace the path of electrical circuits. Power factor is a measure of how efficiently electrical power is being used. A low power factor can cause increased energy losses and reduce system capacity. Power factor correction is used to improve the power factor of an electrical system. Power factor correction involves adding capacitors to the electrical system to offset the inductive reactance. Electrical drawings are used to represent electrical systems. Electrical drawings include single-line diagrams, wiring diagrams, and panel schedules. Single-line diagrams show the major components of an electrical system and their interconnections. Wiring diagrams show the details of the wiring connections. Panel schedules show the circuit breakers and the loads that they serve. The use of proper grounding techniques is essential for electrical safety. Proper grounding helps to prevent electrical shock, reduce the risk of fire, and improve the performance of electrical equipment. Grounding involves connecting the metal enclosures of electrical equipment to the earth. This provides a low impedance path for fault current to flow back to the source in the event of a ground fault. Understanding the principles of electricity is essential for anyone who works with or around electrical systems. Key electrical principles include Ohm's law, Kirchhoff's laws, and the principles of alternating current and direct current. Ohm's law states that voltage is equal to current times resistance. Kirchhoff's laws state that the sum of the currents entering a junction is equal to the sum of the currents leaving the junction, and that the sum of the voltages around a closed loop is equal to zero. Alternating current, AC, is current that flows in both directions. Direct current, DC, is current that flows in only one direction.